How do I stop the angry beeping? Help! Apparently like that. Hello, hello. That has not worked as well as I would have liked. Let me just fix that. My apologies. The hipster look. Everything is sort of half fallen off and broken. Right. That's better. Let's put it on the right window. All right. Hello. It's me again. Sorry. I want to talk about two things. I say extension, but I think these are things that really you all should know, and two things that you will find extremely useful when we are looking at assignment 2. The first of these is testing and how you think about constructing tests. And the second of these is version control. I will touch a little bit more about what this wonderful, wild, magical thing is in a moment. But first, methodical testing. So, things to think about before we begin. We've all written tests that are just a wall full of asserts, just sort of hoping randomly that this thing works, or printing out values. These aren't what I would call rigorous, methodical tests. When you're constructing black box tests, as you would have to do for test game, when you're constructing white box tests in particular, and we're going to use the example of one of the linked list exercises from this week, we're going to look at how we would go about testing that, what we need to know are what we're setting out to do. We need to know our scope. We need to know what we are allowed to test, what we aren't allowed to test, what makes sense, because of course in ADTs, in other places where there is a well-defined interface, a well-specified interface, there are things we are allowed to do, things we aren't allowed to do. We also have to construct, after we've worked out what it is we want to test, scenarios. Consider this thing. Then I do this. What is the shape of the world after that? And not only considering scenarios, just sort of in general, scenarios that may cause things to break. Edge cases, boundaries, places where things can go wrong. And of course, the most important thing, and something that hopefully you will have all picked up by now, is you should be thinking before you test and testing before you set out to implement your code. So what does all this mean? Well, let's actually, once we've got this, what does all this mean? Why are we going through constructing these scenarios? Because now I can really rigorously say how to test something. The first thing you have to have is something you know. Something you know. You can either know this up front or you can construct this yourself. You have some sort of set of things you know to be true. And you want to do this, you want to set this up in a way that means you have as much information as possible available to you. Oh, and the most important thing is, in one scenario, test one thing at a time. Don't try and set out to test all of the things all at once, because not only are units of code valuable things to test, but the ways they interact are valuable things to test. So not only is one unit of code one thing to test, but the interaction of two bits of code. Yeah? So once you've set up this perfect, ideal world, you, of course, pull the handle, run your tests, play a move, change the linked list, whatever it is, and then you go and check that things are where you left them, things are where you expect them to be. It's like going away on holiday and then coming home to find that your entire house has been turned upside down. And every wine glass, every cup, every bowl is just all upside down. It's completely unnerving. So you need to check this. Check pointers, check values. In the case of linked lists, checking the structure, In further courses, there are more rigorous things you have to check for as well. But most importantly, test effectively. Test things that make sense to test. So, that's all just a bunch of words. Let's actually build some tests. What I'm going to do is I'm going to dig up this one of the exercises from this week. If you've already done this, you would have already thought about some of the cases we have to consider. So let's actually try this. Let me hop across. I want list delete tail. So I have already here the tests. I also have a working solution, and I know this solution works. So what I'm going to do is I'm going to set out to write a test from scratch. And just because I am a very strange, very unusual person, I'm not going to use gedit this time, just for the one time, because, radical. I'm going to use my normal text editor. I use a text editor called Emacs. If you're looking at gedit and you're finding, it's getting a little bit sort of not powerful enough, there's a whole raft of other text editors out there, by the way. Emacs I like, Curtis and many of the other tutors like Vi or Vim. There's also other editors out there, as I'm sure you know by now. Okay. Ooh, that is a little bit illegible. Let me... No, that didn't like that. Okay. Well, let me do this. What? Computers are hard, yo. What has just happened? Okay. That's better. Right. And now I can do that, and then that gives me something I can type in. Okay. Apologies for that slight glitch. Now, first of all, what do we know about the function we're setting out to test? Well, let's have a look at the spec for it. It has a well-defined spec, and you can see that out here. What is it? It's somewhere in week 11. Delete tail. Words, 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 words. Okay. List delete tail takes a linked list, deletes and frees the last element of the list. If the list is empty, it should do nothing. There's the prototype. This is all well specified. Yep. The most important thing to grab here, not just the prototype, which we're going to be testing against, but also some information about what it is that we're looking for. I'm going to grab that and just drop it over here. And while I'm here, I'll just do that and include list.h. Now, when you're actually setting out to write tests, you do need a main. When you're setting out to implement these functions, you, of course, should not have a main. Now, I can't actually go any further at this point because what I now need to do is to stop and think about what it is I'm setting out to check. I'm setting out to test this list, delete, tail function. What do we know about it? If I give it the empty list, it does nothing. If I give it a list with one node, I expect that node to vanish. If I give it a list with two nodes, the first node will be intact, the second node will have vanished, and so on and so on. Not only do I want to create those nodes, I also want to have some way of keeping track of them, having as much information as possible. Question up the back there. That's all right, that's all comments for the moment. Comment your code, yo. This is actually a really important thing when you're writing tests in particular. Make sure it's obvious what your test is doing, because otherwise that's not a useful test. God damn it. That's almost worse, isn't it? Why do I live in such a strange world where everything is illegible? All right, stuff the syntax highlighting. I'll just switch to a text editor that doesn't have syntax highlighting. Okay! Also a flavor of Emacs, a slightly less useful one. But with my fewer pretty colors, what do I know about list delete tail? If I give it an empty list, it will do nothing. So let's give it an empty list. The first thing we have to do is construct a list. I'm lazy. So I'm going to just create the list on the stack. This is an interesting and useful way to do it. Things we know. I have a list. It doesn't currently have a head. I now can create a list that I can point to by just taking the address of this. Yeah? And now I can use L, stab, and everything will all work as we expect. Also, because we've got null now in play, I'll include stdlib.h, and while I'm here, I'll grab assert.h. Okay, I have here the empty list. I know nothing should happen as a result of this. So if I now go list delete tail of L, A, my program should continue to exist. This shouldn't cause a program to crash. What else do I now know? Well, I know that the list head should be where I left it. And I can assert that. I can make a statement of assertion here. Remember that an assertion allows me to state something that I know to be true, and if this assertion fails, the program will just disappear. So L, of course, is not null. L stab head will be equal to null. Fairly unsurprising. Okay, so that's one example. That's a pretty dull example. Let's come up with a slightly more interesting one. One of the things, of course, list delete head needs to do is make a free. It's going to delete something, so we need to allocate something. So I'm going to just quickly whip up a create node function. It's going to be static new node. And it'll just take a value, not really too fussed. In fact, I'll give it the 2-argument form. Node next. Node, new node, int value, node next. This is the 2-argument form of node, the new node function takes both pointers. And this is actually fairly useful when you are constructing a linked list that doesn't have a head structure. Our linked lists do have a head structure, but these are still useful nonetheless. New value is value. New next is next. And of course, I return new. So now I can say, well, the one node case if I create a node for that, it's going to have, I don't know, pick a value, pick a nice obvious value, don't pick 0. Put a value there. Now, I'm going to set the list's head, which I already know, to be equal to our new head. So I've created a one-node list, single value, null pointer on the end. If I now do list delete tail, so I've set up my scenario, I now do list delete tail. What do I now know? List head won't have anything in it. So I can assert that. L head is now not null. What can I say about head? What can I ask about head to prove that it's been deleted? Yo.
Is it null?
Is head going to go to null? Head can't have changed. This variable head won't have changed. We don't actually have a way of checking that. Free is one of the things that's very difficult to check. We check this in the auto tests through a horrible, horrible hack that basically looks like this. Saying, yes, this should no longer exist. You don't have to worry too much, but be aware that testing that a thing has been freed is hard without special help like the help that DCC gives us in those tests. Okay, so we've got the one-element list. What about the two-element list? The two-element list is a little bit more interesting. Once again, head, I'm going to create a node. Because, of course, my last node's gone. I've got to create a new one. Don't ever assume anything about the world between tests. It's often a good idea to put whole tests in functions, because you get more assurances about the world having a well-known initial state. I'm also going to define a second thing, and it's going to be new node 42, because 42 is a nice obvious number. Now, if I flip the order of these, actually what I can do is say, when I create my new head, it's next to second. So I've created now a list, which is the node 17, followed by the node containing the value 17, followed by the node containing the value 42, followed by nothing. Yep, two-element list. Again, I now pull the lever. I see what happens. What do I now know to be true? L head can't have changed. L head won't have changed. This is now where we actually have a list left after we do list delete tail. List head should not be null. In fact, we can say what list head should be. It should be head. Fairly intuitively. We also know that L head's value is going to be what we left it as. And we also know where L head should point. L head's next should point to. The node following our first node in this originally two-element list after I delete the tail should be null. Shouldn't be there. That there is the test that you explicitly want. You can also, of course, assert that it's not equal to second. And again, you would, if you had the necessary magic up your sleeve, check that that second node has been deleted. Yeah? But you see, I've applied a rigorous approach here. I've started with something I know. I've started with a whole bunch of statements about something I know up the front. I've made a change to the world, and now I've gone and checked that that made sense. That change has made the world change in the way we expect. Yeah? This is, of course, a really trivial, tiny example. Purely because time, and I don't have the time to write the, 300-odd tests that list insert nth, for example, has. But you can see the approach here. You create a scenario, you construct a change, and then you check that that change has had the effect you expected. Yeah? So this is, of course, also testing one thing only. We've made sure we have enough information as possible. We've held on to the nodes. With longer lists, you can check that all of those nodes are still linked. Using tools like DCC, we can check that things actually have been freed. These are things where having as much information as possible allows us to construct better tests. And then we've gone back, checked the world, and we've used what we know about the world to construct tests that make sense. We know L is not going to go to null. We know that ordinarily we can't actually check for things that have been deleted. So these are some ideas and some general strategies for how to approach testing any sort of function, any sort of interface, any sort of specification. All right? What I've done there, stabbing away at structures, works really well for white box testing, by the way. So if you're setting out to construct white box tests of a function, that is a really, really great way. Reach in, make a change, then reach in and check that that change has propagated in the way you expect. With ADTs, of course, you have to use the interface functions. All right. Let me change tack entirely. Let me change tack to something completely different, which is sharing code. Now, you will have all had to come up with some idea of how between the four of you, between the two of you, you're sharing code. And for assignment 1, you would have had to do the same thing. For this, it's now becoming a little bit less trivial. Quick question. How many of you are using, say, a shared thumb drive that's going around to share code? I've seen it done. It works. Whoever has the thumb drive is the person who's currently making changes. Amazingly, no one here. Email, backwards and forwards replies, long chains of horrible mess. Yep. Again, another way to do it. I've seen it work. Google Docs, I know, is a popular solution. You just chuck all your code in a Google Docs document. There are even more ghetto, bizarre Facebook Messenger. I mean, it works, but surely by this point you've started to run into problems of putting code together. I'm sure that as you started out planning this assignment, you've just gone and sliced and diced the bits of game.c and the bits of test game, and you've gone, these people, someone's got to be responsible for looking after it all at the end, but you can do this part, you can do that part. And you may think you can approach this like you would have approached a collaborative essay or presentation where you just send some person who's finally responsible your bit of the thing to plug it all together. Unfortunately, writing programs, as you've probably noticed, is not like writing an essay. And you've probably started running into the problem of plugging the bits together, and especially with the competition round coming up tonight, you should definitely have a reliable, robust way to plug all those bits together. So you have a game.c that works. So you have a test game.c that works. And there's no frantic panic in the last few minutes to try and put together something that works. So of course, we're computing people. Computing people don't like dealing with the sort of pain of dealing with Facebook Messenger and email threads and shuffling bits of code around and yelling at people when the piece of code they've given us doesn't compile, and oh, it's awful. There is a better way to do it. It's this idea called source code management, or SCM. And you'll sometimes hear SCM referred to as VCS, version control systems, or source code or source configuration management, or revision control systems, they all mean the same thing. And that thing is, you have this really simple set of basic operations. You have a way to create and also remove files, and you have a way of taking a snapshot of the current state of all of your files and directories. And of course, you can then retrieve old code you've written. You can compare your code now with the code that you had yesterday. You can go back to the code you had yesterday in its entirety and work out why it was working and why your code today does not work. But also, version control systems, because software developers don't work in isolation. In the real world, you guys aren't working in isolation. So of course, version control systems are very good at handling collaborators, contributors. Version control systems are all incredibly powerful at letting you track not only who did what and when, but allowing you to get code and give code to others. And there's a whole bunch of options. There's a whole bunch of tools. Like most things in computing, there are many, many options. Text editors, we saw a dozen text editors exist. Version control systems, much the same. There's a whole bunch of centralized and decentralized, and effectively they all just mean, where is the source of all knowledge? Do you need to be connected to the server to make a change? Fairly common in the centralized world, Subversion, CVS for many years. Now, most people have gone distributed, and the tools you'd be using are things like Git and Mercurial, or if you're working in a really expensive organization, a certain G organization who has a small search engine product, you might be using, say, Perforce, or if you're working for someone else, ClearCase, or if you're working at Microsoft, TFS. Actually, Microsoft switched. It should be noted. Microsoft switched. All of Windows is now actually stored in Git. I actually didn't know that until earlier this year. Very interesting bit of trivia there. But most OSs, you would now use Linuxes managed with Git. In fact, that's where Git came from. But they all really do the same thing. They all give you a mechanism for adding and removing files, checking differences, taking snapshots of development. So, why is this useful to you? Well, it turns out that there's a few companies who actually offer private repositories, private sources, private places where you can effectively collaborate with people on your code. Atlassian, GitHub, and GitLab are three really good solutions. I highly recommend all of them. We actually manage the course and a lot of the course materials on GitHub. But I've seen Bitbucket used reliably, and I've seen GitLab used in a couple of other courses. Make sure you make your code private. You can actually get pinged for plagiarism if you don't make your repositories private. And it just so happens Bitbucket gives you free, unlimited, up to a certain point, I think, repositories that are private. GitHub gives you them free if you're a student. You are all students, I hope. GitLab, again, gives you free repositories. We also have a hosted instance here at CSE. And there's also a whole bunch of nice, friendly tools like the Git command interface. Or if you're looking for more friendly tools, there are, of course, a bunch of applications with pretty buttons that you can click. SourceTree works really well with Bitbucket. GitHub for Desktop really only works with GitHub. There's also a couple of other tools. I've heard very positive things about SmartGit and TortoiseGit. And of course, you'll find Git is integrated in a whole bunch of editors and IDEs, so Sublimes, Atoms, VSCs, also things like Xcode and Eclipse and IntelliJ, and if you're using it for whatever reason, Visual Studio, have integration with Git and really with a few other version control systems. I suggest, if you're going to just go and pick up a version control system, I really strongly suggest starting with Git. There's a really great demo up, thanks to the lovely folks at GitHub, try.github.io. Quick 15-minute or so walkthrough of the Git commands. I'll go through some of them in my system here in a moment. But there's also, of course, a whole bunch of documentation online, Git SCM. You can Google and ask. And most of your tutors are versed in using Git reasonably well. So Git is a fairly good choice if you want to just get started quickly and work collaboratively and productively. So let's have a look at what a Git repository looks like. Now, you know I was saying that course materials are all managed on GitHub. Obviously, they're all in Git. And if I pull up one of the prettier tools, this is a nice little tool called GitG, I can actually look through and see the history of what has been happening. I do love having the first lab of the week, by the way. For those of you who have seen the often frantic panic in the first lab of the week, that's, yeah, usually what I'm frantically fixing on a Monday afternoon. But you can see through people, various tutors are contributing all together. Andrew's also got a sort of stuff that's going in here, all wonderful. So how do we actually use a tool like this? There's a whole bunch of great commands that we can use. The most obvious thing, of course, is you will need to create a repository. I have Git repositories everywhere. Some shells will actually tell you what repository you're in. I'll just call mine repo because I'm feeling lazy. Okay, and of course there's nothing here. There is absolutely nothing here at all, except, I don't know, the directories above us, and this new directory that's just appeared here called .git. Don't touch your .git directory. It's super bad for you. Bad things will happen to you and your code if you do. Okay, so this repository isn't very interesting. If I grab GitG again to have a look at it, there's nothing there. Clean and empty, wonderful, perfect place to begin. I'll even say, oh, there's nothing there. With Git, I can add files. I can create and add files. So let me grab that file I was working on earlier. I'll grab that here. So there's a file I've just pulled out of my hat. I can use Git to track this file. I tell Git I want to add this file. And Git goes, yep, okay, cool. Sounds good. Now, that's all very well. Now you need to take a snapshot of the current state of affairs. I can actually ask Git for what things currently look like by saying, hey, Git, what's the status of things? And it says, there's no commits yet, but there's this new file, and you can just barely see that in the horrid green that it chooses. So I'm going to commit this. I'm going to take a snapshot here. This snapshot won't change. A good rule of thumb is to take these snapshots every time you have something that works before you then go and break things again. So I'm going to commit. Git commit. In this case, I'll say -m, and in double quotes, I'm extremely lazy. This is called initial commit. And it'll tell me, yes, a commit was created. Okay, so that's all very nice. What if I want to change my code? Let's say, well, that test obviously doesn't work anymore. You should never remove tests, by the way, don't do that. But now I can ask Git, having made a change, something got changed in that lurid red there. It marks that that file has been modified. And again, I would add that again. And now, again, I can commit this. I can take a second snapshot. Probably useful to pick better commit messages than these, of course. Be descriptive in your commit messages. Tell us what it is that you've done. Okay. Let's have a look in GitG again. GitG, it's marvelous. And you can just see up there in tiny little print our initial commit. And here it is. We created some files, 56 lines of code. there they all are. And you can scroll through and you see they're all marked with a plus. They're all marked added new in this revision. In this snapshot, these were added. And here in this snapshot, the lines marked in red there, those were removed. That's really nice. And if you're wondering why the green and red, and where you may have seen this before, this is actually the same mechanism, or very, very similar mechanism, to autotest, and the way autotest shows us differences. So this is all really quite nice. But let's say I want to work on something, and I want to collaborate with people. I'm going to create a quick little repository. I'm going to create a repository out on GitHub. I'm going to make it private. The easiest and fastest way to do that, of course, is from the GitHub website. Blah, 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 blah. Cool. And I can go, okay, yes, create me a repository. Make sure it's private, of course. I won't initialize it, just needs to be private, just needs to have a name. In fact, I'll make this public in a moment. And Git will handily tell you how to get started. In this case, I'm just going to take an existing repository that I have and commit it. These are two incantations to say, hey, someone else has a slightly more authoritative, maybe, version. Or maybe I want to use this place as a place that is a central place of wisdom. And now what I do is I say, hey, take my idea of what the master state of code is and push that to the place that we've set, our origin. And it will think for a bit and go, okay, I can do that. Most of you will start out with an HTTPS URL. You'll have to enter your username and password each time. The Git documentation, and particularly the documentation on GitHub, shows you how to make that go fast. You don't have to worry too much about passwords. Yes. Sorry, I forgot my password there. Okay, so that's all very nice. Let me go and create a second copy of this repository. And what I'm going to do is I'm going to clone this repository. I'm going to pull down a second copy of this repository from our master source of wisdom. This also does the setting up of where the original source of wisdom is. Incidentally, every Git repository is a full history of that Git repository. So if I'll now use the git log command, and it will tell me that these are some commits that were made on this repository. Okay, that's quite nice. To make it obvious, I'll change my email address so you can obviously see that this repository produced this commit. And now, now if I go and edit this file again, I'll put that test back because that was a bad idea. We know that this is now true. Again, git status will tell us we've got a change there. I add that. I can commit that. And now I can push this. In the same way that we saw before, we have somewhere we can push this to. And if I pop over to GitHub in a moment, you can actually see on GitHub, for example, what this repository might look like. So there it is, 3 commits in this repository, 1 branch, 1 contributor. And I can go through, look at the history of this file, the commits that went into this file, and also this great little feature here, blame. It does exactly what you think it does. Lets me go through and look at who changed what when. Okay, let me now hop back across to my other copy of this repository. When there are changes upstream of me, I can pull those changes in. And of course the command, as you probably would have guessed at this point, is git pull. And this pulls down from the remote all the new commits, all of the new snapshots of history that have been made, and if you look there, there is that change that we just made. And now if I actually look, just to demonstrate my point, git log will tell me that the other repository made that commit. So I have two complete sets of the history, all of the history of this project. I say project very loosely here. I have a private way to share this between other people, and I have a nice way to keep track of who's made what changes and when. I'm not going to say you should immediately switch to using Git, because that's probably a bad idea. Immediately dropping everything and going, yes, we'll go and jump on Git, with just on 2 hours before a competition runs, probably not a good idea, but probably shortly after that, you might want to think about how you do this. You can have people making commits, these changes to the same file, the same game.c, the same test game.c, the same player.c can live in a repository, and you can see, how that file changes over time. You can have a collaborative and really, really powerful way of keeping track of what the current state of good code is. There are, of course, going to be problems. You have to negotiate the weird and wonderful world of